Sorry, forgot to unmute. Here we go.
Yeah,
can you see my screen?
well.
Yeah. Cool. Right. Thanks, Mike. And yeah, thanks, Alberto. It must be really late for you. I'm amazed you're still awake. But good for you. So yeah, today I'm just going to present some results of some data analysis we've done of wave attenuation in the Ross Sea, in the marginalized zone during the Piper's voyage. So what motivated our analysis here is that there has been a lot of observations and modeling as well done that, so first of all, confirms that the wave energy attenuates exponentially in the marginalized zone, and the attenuation coefficient here, this parameter alpha, seems to depend on frequency of wave period according to some kind of power law, which is presented here. Now the question here, of course, is what power is that? And there has been a lot of work, especially led by Mike in recent years, looking into that. So there has been some observations of that, and here is a plot from one of Mike's paper looking at several data sets of wave attenuation in the marginalized zone, and they found essentially that the range of beta values would be between 2 and 4, very broadly. Now there has been also some efforts to try to predict what this power law could be out of a model. And here the range is much wider. So if you consider a viscoelastic type model where the whole ice sheet is modeled as some kind of a viscoelastic layer, uniform one, then depending on the rheological property of the ice, then you can basically model a whole range of behavior with a power law that varies between 2 and 11. And now if you restrict yourself to scattering models, so that was, again, work done by Mike recently, he found that from a couple of models, this power seems to be between 8 and 10. So clearly there is a mismatch here between theory and observations. So here we just want to add essentially to that from the observational point of view. And there are a couple of questions that come out of that. The first one is the hard one, I would say, and how does this power law relationship describing how the attenuation coefficient depends on the wave period emerge out of the physical processes that govern the ice-induced attenuation of waves in the marginalized zone? And I'm not going to deal with that today, but the second question is, how does this power itself, how does it depend on the state of the system, on the ice properties, on the wave properties, and possibly even atmospheric properties? And that's really the question I'm going to try to focus on today. So the way we've done that, so I was not on this experiment, but my colleague Alison Kohut at NIWA here in New Zealand designed the experiment, and Letty Roach, also co-author on this paper, she actually was on the ship and deployed the wave buoys. And so there was some wave buoy deploys in the Ross Sea. That was in 2017, I believe, and there were quite a few of them. I'll get back to that a bit later with more description, but we were able to know, of course, the location of the buoys and these return spectra every 15 minutes. So we also wanted to understand the impact of ice concentration. So we looked at the climate data record from NSIDC. So here the spatial resolution is 25 kilometers, and the data are updated every day. So that's from satellite measurements. We also looked at open ocean wave data, so out of the ice. Looking at wave watch output, so from the NOAA NCEP Hindcast, sorry. So here with a spatial resolution of 0.5 degrees and time resolution of 3 hours. And we also looked at the possible impact of wind. And here we look at the ERA 5 reanalysis data, which were given in the spatially resolved and also temporally resolved scales. Right, so before I get into the details, let me first describe the take-home message right away. So it turns out that ice concentration and the mean wave period are the two main quantities which seems to explain the variability in the power beta in the power law. So to be more specific, we identified 3 regimes in our analysis. So in the first regime, where we found that in low concentration and we had short and intense waves, in the second regime was more like a mid-range concentration and also mid-range period. And in the third regime, we had high concentration, nearly 100%, and very small and long waves. And so what we found is that the power in the first regime was about 3, in the second it was about 2 consistently, and in the third one it was actually less than 2. And I'll get back into that later. So that was the main finding, but the other finding which was interesting and that we did not really anticipate at the start is we found an impact of the wind, and not the wind speed, but the wind direction seems to be a better predictor of an impact on the power law relationship. And so actually what we find is that the power itself was not affected by the direction, but the wind direction affected the magnitude of the attenuation itself. Right, so what did we do? Well, I was not involved in that, but my colleagues deployed 14 wave buoys in 2017, and they stayed there for a few months, as you can see here, and they recorded a range of so wave condition and also in the range of ice conditions. So one limitation is that the wave direction was not recorded. So I'll attempt to show you an animation showing the deployment. So I hope you can see that. Oh, no, I want to make it bigger. There we go. So here we had 4 buoys deployed in April, okay, and these drifted north, but the ice grew a lot at the same time, actually. So these did not become closer to the ice edge. Actually, they get deeper, even though they move north. And then a little bit further, so let me move a little bit forward in time. So in early June, which is going to happen now. So another set of 10 buoys was deployed here. So that's when the ship left the marginalized zone. And this gives a lot, of course, a lot more data. And this drifted way north as well quickly. And as you can see, they also spread zonally, horizontally, which made it difficult to extract attenuation from it. But the ice stopped growing as well at the same time. So this became really close to the ice edge, actually. All right. So like I said, a range of ice conditions. So these were photos taken during the deployment. As you can see, we have some small flows here, or even some buoys were deployed on continuous ice. So if you're wondering, the buoys were actually these small yellow boxes here, which actually sat on the floe as opposed to being floating directly in the water. All right. So then what we did, the standard analysis of wave attenuation. So we had to make a couple of assumptions since we didn't know the wave directions. So we assume waves travel directly from north to south. We assume stationary conditions. So we looked at the spectra at the same time in 2 different points. And we assume that waves attenuate exponentially. And so we have wanted to extract this alpha here, the attenuation coefficients. So we make a couple of assumptions, assuming that alpha was positive. So we discarded all the wave growth that were observed in some cases. And we also limited the zonal spread. So as you could see in the animation, in many cases, the buoys spread horizontally a lot. So that way they were too zonally spread. We didn't consider that because we figured that probably didn't measure the same wave event between 2 buoys. And then we looked at all the different pairs of buoys which respected these conditions. And assuming exponential attenuation, we can simply recover the attenuation at different wave periods. All right. So we obtained a lot of data out of that. So from the west deployment, so that's when we had 4 buoys deployed. We obtained over 51,000 estimates of attenuations. And in the east deployment, when we had another 10 buoys deployed, we had nearly 180,000 attenuation estimates. And so when we put all that into plots, so that's the attenuation coefficient as a function of wave period here, and bin that into integer wave periods, that's what we obtained. So we had a wide spread, but we can still see some kind of trend here of the attenuation seems to decrease with wave period, all right, which is what we expect. So if we just now look at the same data, but we're just at the median, so this is what it looks like. So we can see actually that the two data sets were actually consistent for wave period over 12 seconds, okay? And then we have something interesting happening here for smaller wave periods, where we have some kind of kink here in the curve, and that was a little bit hard to explain. So anyway, we went with that at first, and we fitted power laws to try to extract the power. So when we did that for the West data, we found that actually a power of -2 over the range 7 to 21 seconds gave a reasonably good fit. But then you can start playing around with, is it an appropriate range for the fitting? So if we instead fit over a smaller range of wave periods, so here 10 to 16 seconds, we find a power of 2.5, which is quite a drastic change. And then if we do the same thing for the East data, so over the whole range we find of wave period, we find a power of 1.5, which is quite small and smaller than what's been previously observed. But of course, here the question is, does it really look like a power law? I mean, if you look at the curve and, there is clearly a change here, like a local maximum. So, maybe it doesn't make sense to try to fit a power law through that curve, right? So what we found here was the power law seems to be on the lower end of the values which were previously observed, which, remember, at the start I mentioned was 2 to 4. Here it was more like near to 2 and even lower than 2. But it seems to be also quite sensitive to the range of wave period over which we perform the fit. So the question is that, are we fitting to too much data here? So we had the whole range of wave, ice, and atmospheric conditions here, all put into this one curve, right? So maybe we should try to look at the impact of different conditions. So this is what we did, and we looked at what happened when we bin data in terms of ice concentration, and we look at the impact of wave, significant wave height and mean wave periods, and we also look at the wind conditions. And I'm not going to give you all the details of this analysis. The paper just got published online last week, so that gives you a good excuse to have a look at it. If you want to look at all the details here of how the attenuation and the power law fit performs for all, when we look at the impact of all these possible drivers. But the main findings here is that ice concentration, mean wave period, and wind direction seem to be the key 3 drivers here of this power law relationship between alpha and wave period. In particular, we found that at low concentration, the power were close to 3, actually, and at high concentration, it was less than 2. Now, in terms of mean wave periods, so for mean wave periods, less than 14 seconds, it was again close to 3, and for mean wave periods larger than 14 seconds, it seems to be again less than 2. While, as I mentioned before, so when we look at the meridional component of the wind vector, that seemed to affect the magnitude of the attenuation, but not the power beta. So in particular, when we had wind blowing north, that seems to enhance the attenuation, while when we had wind blowing south, it reduced it in magnitude. So we seem to have like similar behavior for concentration and mean wave period actually here. So of course that suggests maybe that the two are correlated to each other. So I'm just going to focus on that to finish the talk here. If we look now at a scatter plot of all our attenuation estimates, but as a function of both sea ice concentration and mean wave period, it looks like that, and that's for the east deployment alone. And what we found interesting here is that there seem to be 2 clusters of points, which I identify here in blue and greens. And what we really didn't expect, and we found really interesting, is that when we added the data from the west deployments, then they fit right here in this plot, right in the middle. So they seem to bridge the gap here between these 2 regimes. So we actually take that as a third regime. And now we try to analyze here the attenuation as a function of wave period over each of these three regimes to see what we find are the curves we obtain. So the solid curves are for wind that is blowing south, so for northerly dominant wind, and the dashed curve are for southerly dominant wind. And as you can see here, so the wind has the effect of shifting essentially the curve up and down, but without affecting the slope of the curves. Now, what we did, of course, here is also fit power law in regions where it kind of makes sense to fit power laws. And we obtain these relationships here in the tables. So we can find beta in regime 1 seemed to be close to 3. In regime 2 was around 2. And in regime 3, it was 1.5. Now, you can see the range of wave period over which the fit was performed here is quite different, okay? So for example, this first regime here seems to be only applicable for small wave periods, while the other two are over a much broader range of wave periods. We also looked at other quantities such as the significant wave height and the distance from the ice edge to try to qualify a little bit more these three regimes. So regime 1 in particular seems to represent observations of waves which were quite intense. So we had a mean significant wave height of 5.5 meters, which is really high. And the mean distance to the ice edge was about 40 kilometers as well. So they were fairly close to the ice edge. And as we go into regime 2 and regime 3, we're going deeper and deeper into the ice edge, and we observe waves which were much less intense, with a significant wave height less than 1. All right, so just to wrap up, so what I'm really interesting here and to find is that this power, the power law relationship between attenuation and wave period, I think what it shows here is that it depends on the conditions, on the ice, wave, and even potentially wind conditions. And so finding a universal power that qualifies attenuations for all kind of ice is very unlikely. And so if we want to now parameterize wave attenuation in wave models due to the presence of ice, then maybe a piecewise law would be better as a function of different ice and wave conditions, say. So yeah, I did not talk about that in the talk, but that's a finding also, if you want to have a look in the paper, is that we find that the attenuation rate does not increase with ice concentration. So this is actually different from the way it is currently parameterized in wave models such as WaveWatch 3, where attenuation is assumed to depend linearly on the ice concentration. And here I did not find these trends. So that's maybe something to think about for future models. And finally, I believe this is also the first observations of how the wind, and in particular the wind direction, affect attenuation. And so maybe that's also something to consider. So of course there were some limitations. There are other possible drivers that we did not consider, such as the ice thickness and the flow size, which we've heard about in the last few talks. And one key limitation of our analysis is that we did not have access to the wave directions. We assumed the waves were traveling directly from north to south. We tried to correct for it using directions output from wave models. That did not give us some positive results, so we had to give that up. Again, we give some details about that in the paper. So yeah, so have a look at the paper, and thank you, and happy to answer your question.
Thanks a lot, Fabien. We're just time's pretty much up. So we'll just have one question, if that's all right, and then there's one quick question.